As we've already seen, the total energy of a harmonic oscillator cannot be smaller than a specific value, which is equal to half of h bar multiplied by the oscillator's frequency. Previously, we derived this value, known as the zero-point energy, by analyzing the oscillator's motion in a coherent state. Now, we will demonstrate that the existence of zero-point energy is not confined to coherent states. It is, in fact, intimately connected to the uncertainty principle. Consider a simple harmonic oscillator near its equilibrium state, where both its displacement and momentum are very close to zero. Let's examine the oscillator problem within the framework of classical mechanics, with quantum mechanics entering the discussion primarily through the uncertainty principle. We'll denote the displacement from the equilibrium position as delta x, and the deviation of momentum from its equilibrium value, which is zero, as delta p. In a broad sense, we can view our oscillator as fluctuating around its equilibrium state, where delta x and delta p represent the extent or uncertainty associated with these fluctuations. The total energy E of the oscillator consists of two parts, kinetic and potential. The kinetic part is proportional to the square of delta p, while the potential part is proportional to the square of delta x. In classical mechanics, the expression for the total energy can result in zero when both delta x and delta p vanish, indicating a state of precise equilibrium. However, in quantum mechanics, delta x and delta p cannot simultaneously be zero, as the Heisenberg uncertainty principle requires their product to be greater than or equal to half of h bar. So, the question we want to address is this. Considering the restriction imposed by the uncertainty principle, what is the smallest possible value for the total energy of the oscillator? To find the minimum energy, let's consider the following expression: delta p divided by the square root of 2m minus the square root of m over 2 times omega delta x. Clearly, the square of this expression cannot be negative. Let's take this inequality as our starting point. Expanding the square on the left-hand side, we obtain the following three terms. The sum of the first two terms is easily recognized. It's simply the total energy of the oscillator. By moving the third term to the other side of the inequality, we deduce that the total energy cannot be smaller than the oscillator's frequency multiplied by the product of delta x and delta p. Additionally, in accordance with the Heisenberg uncertainty principle, the product of delta x and delta p must be greater than or equal to half of h bar. Combining these two facts, we arrive at the following conclusion: the oscillator's energy cannot be smaller than half of omega times h bar. This, of course, is the same zero-point energy we encountered earlier when studying the motion of a coherent state of the harmonic oscillator. Now, we can better understand the physical origin of zero-point energy and its connection to the uncertainty principle.